Welcome everyone to the seventh lecture of States of Matter. Myself Varad Daoo. I'm a doctoral student at the Department of Chemical Engineering at Kanpur. So the previous classes we have touched upon the we have studied about various gas law models, right? We have also studied about ideal gas law. Then we have also touched upon the kinetic molecular theory of gases. We have studied its postulates, and also for some of the postulates we have also studied a justification for that. Right. So today we are going to continue that, and and we are going to study about kinetic gas equation and the origins of various gas laws, that is Boyle's law, Charles law, and Dalton's law from the molecular theory approach, right? That is what we are going to study. So this is lecture 7, states of matter. Okay. And the first topic which we are going to study is justification for the justification for the postulates of kinetic molecular theory of gases. We in the previous class we have studied the first four postulates. Now we are going to study the fifth. The fifth justification is, it is common observation that the gas expands when the pressure on the gas is released. The expansion of gas means the movement of molecules away from one another and increases the void between them. This is possible if the attractive forces between the molecules are negligible, right? So it is a common observation that expands when the pressure on the gas is released. The expansion of gas means the movement of molecules away from one another and increases the void between them. This is possible if the attractive forces between the molecules are negligible. The sixth point is, when the gas is enclosed in a vessel, its molecules being in rapidly motion constantly go on striking the walls. As a result, the wall experiences some outward force, and this force per unit area is termed as gas pressure. Okay. So when the gas is enclosed in a vessel, its molecule being in rapid motion constantly strike on the walls, go on striking the walls. As a result, the walls experience some outward force, and this force per unit area is called as gas pressure. The seventh and the last justification is, due to molecular collisions, the different gas molecules have different speeds. As a result, the molecules have different kinetic energies. Under these circumstances, it is assumed that the average kinetic energy is directly proportional to the absolute temperature. Right? Due to molecular collisions, the different molecules have different speeds. As a result, the the molecules have different kinetic energies. Right? Under these circumstances, it is assumed that the average kinetic energy is directly proportional to the absolute temperature. It has been observed that when the gas is heated, its temperature rises. This is because of the fact that thermal energy results into increase in average kinetic energy of gas molecule. Therefore, these molecules strikes the wall of the container more frequently and thus exert more pressure. Therefore, it is seen that on heating a gas at a constant volume, the pressure increases. Okay. It has been observed that when the gas is heated, it has been observed that when the gas is heated, its temperature rises. This is because of the fact that thermal energy results into increase in average kinetic energy of the gas molecules. Therefore, these molecules strike the walls of the container more frequently. This molecule strikes the walls of the container more frequently. right? And thus exert more pressure. Therefore, it is seen that on heating a gas at a constant volume increases the pressure. The pressure increases. Right? The next topic which we are going to see is kinetic gas equation, right? On the basis of postulates of kinetic theory, an equation was derived for the pressure of the gas, and this equation is known as kinetic equation. On the basis of postulates of kinetic molecular theory, an equation was derived for the pressure of the gas, and this expression is known as kinetic gas equation. This is P into V 1 by 3 m n into U square, right? Where n is the number of molecule in volume V, right? So V is the volume, m is the mass of the molecule, U is the velocity known as root mean square velocity. Next topic is average kinetic energy of gas molecules. Using the above relationship and gas laws, the relationship between average translational kinetic energy of a molecule at a temperature T of the gas can be derived. The average translational kinetic energy of a molecule is half mu square at a temperature T. Right? So the average translational kinetic energy of a molecule is half mu square, where u is the root mean square velocity at temperature T. Right? For n molecules, this expression is going to be, for n molecule, we have Ek is equal to half m into n into u bar square, right? The kinetic gas equation is, right? So let us put this as expression 1, right? And this as expression 2, right? So we can write PV is equal to 1 by 3 m n u square bar, right? On rearranging, what we get, PV is equal to 2 by 3 into 1 by 2 into mn u square bar. Therefore, PV is equal to 2 by 3 Ek, right? This is going to be the equation 3. So comparing this equation, comparing equation 3 with general gas equation, we get PV is equals to RT for 1 mole of gas, right? Hence, what we can say is RT is equals to 2 by 3 Pk, or in other words, Ek is equals to 3 by 2 RT. Let's say this is equation 4. Similarly, kinetic energy for n moles of the gas, n moles of the gas is nothing but Ek is equals to 3 by 2 nRT. This is expression 5. Hence, the average kinetic energy per molecule can be obtained by dividing both sides of this equation by Avogadro number. Right? right? Therefore, average kinetic energy for one molecule is going to be 3 by 2 RT by Na, which is nothing but 3 by 2 kBT, where kB is called as Boltzmann constant. And its value is going to be R by Na, right? Hence, what we have proved is Ek is equals to 3 by 2 kBT, which implies Ek is directly proportional to temperature, right? Hence, average kinetic energy of a gas is directly proportional to its absolute temperature, irrespective of its nature. Right? This is also one of the assumptions of kinetic molecular theory. Hence, hence, average kinetic energy of a gas is directly proportional to its absolute temperature, right? Irrespective of its nature. Right? This is also one of the assumptions of kinetic theory, right? Now we will know that since we know that kinetic energy is going to be proportional to temperature, but temperature is going to be proportional to the square of the velocity, right? Therefore, but kinetic energy is also proportional to the root mean square velocity, right? Therefore, u square is proportional to t. Therefore, u is proportional to root t. This is also one of the most important, right? Now, the next topic is explanation of gas laws on the basis of kinetic molecular theory of gases. Kinetic molecular theory of gases. Okay. So the first law which we are going to study is Boyle's law, right? So according to kinetic molecular theory, the pressure exerted by a gas is due to striking of the molecules of the gas on the walls of the container, right? Which is nothing but postulate 4. Therefore, it depends upon the number of molecular impacts or collision per unit area per unit second on the walls. If the temperature is kept constant, the average speed of the molecule remains the same, as kinetic energy is directly proportional to temperature. Now, if the volume is increased, there will be less number of molecules hitting each unit area of the containing vessel in unit time. Consequently, the pressure will decrease, right? So let us write this down. According to kinetic molecular theory, the pressure exerted by a gas is due to striking of the molecule on the walls of the container. This is nothing but postulate 4. Right? Therefore, it depends upon the number of molecules, number of molecular impacts, right? Or collision per unit area, per unit time. Right? Now, if temperature is kept constant, right? Then the average speed of the molecules remains the same. Molecule remains the same as half mv square is directly proportional to temperature, right? Now, if the volume is increased, right? Now, if the volume is increased, the number of molecules hitting each unit area of the containing vessel increases, right? Is increased, there will be less number of molecules, hitting each unit area, each unit area of the containing vessel in a unit time, right? Consequently, the pressure should decrease. Consequently, pressure will decrease, right? For example, if the volume is made double, the number of molecules striking the unit area of the wall will become all about half. As a result, the pressure of the gas will be reduced to one half of its original value. On the other hand, if volume is decreased, there will be more molecules in a given volume and hence the pressure will increase, right? Thus, it can be concluded that any given temperature, the pressure exerted by a gas is inversely proportional to the volume, and this is nothing but Boyle's law, right? Thus, it can be concluded that at given temperature, the pressure exerted by a gas, the pressure exerted by a gas is inversely proportional to the volume. Boyle's law. This can be easily proved with the help of a kinetic gas equation, right? So what we have is we have derived from the kinetic gas equation that mu square bar is nothing but 3 by 2 kt, right? And we also know PV is equal to nothing but 1 by 3 and mu square bar, right? Therefore, we can write PV is equal to 2 by 3 into 1 by 2 into n by v, right? Into mu square bar, right? Hence, what we can do is PV is equal to 2 by 3 into n by v into 1 by 2 mu square bar, right? This is nothing but 2 by 3 into n by v into 3 by 2 k into t, which implies nothing but, or PV is equal to n kt, right? This is nothing but constant. Hence, we can say is P is inversely proportional to V, right? Right? This is nothing but Boyle's law, right? Now let us understand number 2, Charles' law. When the temperature of the gas is increased, the kinetic energy of the molecules increases because half mv square is directly proportional to temperature. As a result, the velocity of the molecule increases, and consequently they collide with the walls of the container more frequently and more vigorously. Therefore, the pressure of the gas is expected to increase. However, if pressure is to be kept constant, the number of molecular collisions on the walls of the container must be kept constant. This is only possible if the volume of the gas increases, right? That is, gas expands. On the other hand, if temperature is decreased, the average velocity of the molecule decreases and therefore the pressure decreases. To keep the pressure constant, the volume of the gas must decrease so that the number of collisions per unit area remains the same. Thus, we can conclude that at a given pressure, volume of the gas increases with rise in temperature and decreases with fall in temperature. Hence, volume is directly proportional to the temperature at constant pressure, which is nothing but Charles' law, right? Let's write this down. So we can easily prove it from the kinetic gas theory, right? So what we have is PV is nothing but 2 by 3 into EK, right? But EK is directly proportional to temperature, right? Therefore, PV is also directly proportional to the temperature at constant pressure. What we have is V is directly proportional to temperature, and this is nothing but Charles' law. And this came because at given pressure, volume of the gas increases with rise in temperature, right? And decreases with fall in temperature, right? The third law is nothing but Dalton's law, right? The pressure of the gas is due to the striking of the gas molecules on the walls of the container. Because of the absence of attractive forces, the molecules of each gas behave independently of the molecules of other gas in the mixture. Therefore, no molecule is influenced by others in its collision with the wall of the container. The molecules of one gas contribute toward the total pressure as if the molecules of the other gas were not present. Thus, the total pressure of a mixture of gas would be the sum of the partial pressure of the gases, right? This is not even Dalton's, right? So we should write this down. The pressure of a gas due to the striking of the gas molecule on the walls of the container. Because of the absence of absence of attractive forces, the molecules of each gas, the molecules of each gas behave independently of the molecules of the other gases in the mixture. Other gases in the mixture. Therefore, no molecule is influenced by the others in its collision. Therefore, no molecule is influenced by other in its collision, other in its collision with the walls of the container, right? Walls of the container. The molecule of one gas contribute towards the total pressure. The molecule of one gas contributes toward toward the total pressure as if the molecules of the other gas were not there. Molecules of other gas were not there. Thus, we can say that the total pressure, the total pressure of a mixture of gases would be the sum of the partial pressure of the gases, and this is nothing but Dalton's law, right? The next topic is the Maxwell-Boltzmann distribution. Maxwell-Boltzmann distribution of molecular speeds, right? So gas consists of tiny particles separated from one another by large empty spaces, and these particles are constantly moving in all directions. During their motion, they collide with another and also with the walls of the container. As a result of the collision, the speed and direction of the molecules go on changing. Thus, all molecules present in the given sample of a gas do not possess the same speed, right? You should write it down. All the molecules present given sample of gas do not possess the same speed, right? The speeds of individual molecules are different and are distributed over a wide range. Even if all the particles had same speed, due to molecular collisions, they will have different speed, right? So let us write this down. That the speeds of individual molecules are different and are distributed over a wide range. And are distributed over a wide range. So even if all the particles had the same speed initially, due to the molecular collisions, they will have different speeds. Right? The speeds of different molecules also go on changing. However, the distribution of speed among different molecules remains the same at a particular temperature, although the individual speeds of the molecules may change. Okay? This is very important. That the speeds of different molecules, the speeds of different molecules, the speeds of different molecules also go on changing. Go on changing. However, the distribution of speeds, distribution of speeds among different molecules, among different molecules remains the same, remains the same at a particular temperature, at a particular temperature. Although the individual speeds of the molecules may change. Right? Thus, the fraction of molecules with a particular speed remains constant, and this is known as the distribution of speed, and also known as Maxwell-Boltzmann distribution law, because they were the first to formulate it. Right? Thus, what we can say is, thus the fraction of the molecules with a particular speed remains constant. Speed remains constant, and this is known as distribution of speed. This is known as Maxwell-Boltzmann distribution law, right? Distribution law. So the important features of so is known as Maxwell-Boltzmann distribution law, right? So in this class, we have seen the remaining postulates of kinetic theory of gases. Further, we have also seen the kinetic gas equation, and then we have derived the expression for pressure volume relationship in terms of molecules. Then we have also found out the relationship for the average kinetic energy of the molecule. We have then clubbed together this, and then we have proved that the kinetic energy is directly proportional to temperature. Further, we have also seen the explanation for gas laws like Boyle's law, Charles' law, and Dalton's law based on this kinetic molecular theory of gases. At the end, we have also introduced the Maxwell-Boltzmann distribution of the molecular species. So in the next class, we are going to study in detail about this Maxwell-Boltzmann distribution curve, and we are also going to study about the effect of this effect of temperature on the distribution of speed. Further, we'll also see the different speeds which we have, that is the most probable speed or the average speed or the root mean square velocity, right? But so thank you all for attending this class, and I hope to see you again in the next class. Thank you.